So let's get started. Midterm, as you know, is in a week from today in class. Bring the other half of your 8.5 by 11 piece of paper, your cheat sheet from the previous midterm. You can, as before, write whatever you want on that. Somebody asked this question before. We're not going to use this as sort of a cumulative midterm. We're really planning on just testing you on what you've learned in this sort of middle third of the class. So you hopefully won't need the other side of the sheet. But the equations that we'll give you will more or less be cumulative. So we'll basically take the equation sheet that we had before and we'll just add more equations to that. So in principle, you won't need to bring your own cheat sheet. And obviously, in terms of constants and things, we'll give you all the numbers that you need if we ask you to actually do a calculation. So do bring a calculator, pen, pencil, etc. It will be in this room. So I'm sorry for the small writing area, but hopefully you can deal with that. Any questions about the midterm?
So just to clarify,
yeah.
Half a cheat sheet, half a sheet of paper means cut it in half? Or
No, the other side.
Just one side?
Yeah. I don't know, what should I say? Other side? Something.
One side?
One side of a cheat sheet. Thank you. I couldn't come up with the right words. Right, so that's all I wanted to say about that. You will be responsible for all the lecture material. You will be responsible for all the lecture material, all the problem sets, all the section material, all the reading from the last midterm. So it's a big amount to study. You have a homework due on Tuesday in class at 11 a.m. Please bring that and give it to me before the beginning of class. And the talc for that will be Monday night. The review will be the normal talc time, and that'll be from 5 to 7, run by one of the GSIs. And the reading for basically next week, the one class that we have before the midterm will be 25.1 and 25.2. There's no colloquium today, so you're all off the hook. So are we. We've had many, many talks. It's sort of debilitating. But we're closing in on our faculty hires. So you'll hear about this very soon. It won't make like the New York Times, but we're very excited about the people that we're thinking about. Any questions about logistics?
How many professors will the astronomy department have?
So we have 11 or 12 what are called full-time employees. We have a bunch of other people who have sort of joint appointments with other departments and other research labs. So we have about 15 or 16. It's a reasonably small department as departments go in the US. Okay, so last time we talked about the kinematic mass of the Milky Way. And that's something that we can determine interior to any radius at which we can measure a circular velocity. In particular, for our own, we wind up getting a mass in stuff unseen much larger than the stuff seen, or actually the stuff inferred from the stuff seen. That is, we count up all the stars, we count up all the gas, all the mass associated with the gas, and we actually take a distribution of stars that might actually fall below our detection level. But if I measure one sort of star that's similar to our own with a solar mass, I know approximately how many stars there are of a half solar mass, or even 1/10 of a solar mass. And so you can sort of do that full cost accounting, and you still don't come up with nearly enough mass to account for what we see from the rotation curves. Anytime we're able to measure a distance from us, here's the galactic center, here's the sun. If we measure the velocity of how some parcel is moving around the galactic center, however we wind up doing that, there's going to be some radius, galactocentric radius, some r0, and some distance. And remember, we define this as an angle L from the galactic center along the galactic plane. If we have a way of making a measurement of what that velocity is, then we have a way of making a measure of the velocity as a function of radius, galactocentric radius as it's called. And that circular velocity for the Milky Way looks to be something like this. we said that interior to about 2 kiloparsecs, the velocity appears to be proportional to r. And we said there's some sort of leveling off at around 220 kilometers a second. And here we are at 8 kiloparsecs. And this leveling off continues on to very large numbers of kiloparsec, dozens of kiloparsecs, if not 100 kiloparsecs. There aren't a whole lot of stars beyond 25 kiloparsecs. So it's the H1 gas at very large distances that gives us this inference of a flat rotation curve. In trying to understand what this dark matter is, we went through a nominal exercise to figure out how we might infer what the mass density is within the plane, at least the mass density below the sun. We can infer the velocities and the accelerations of stars near us. And we said that the acceleration towards the disk, remember in this z direction, in the way that we wrote our location above and below the plane in cylindrical coordinates, is not enough to account for the dark matter needed to give us the rotation curve where we are. Instead, what we said that dark matter is in the form of a halo, roughly spherical, and it has some parameterization as a function of r. Now, where r is going not just around the galactic center, but at any angle above and below the plane, whatever that distance r is, goes something like some constant c0 a squared plus r squared. And I gave you what those constants were last time. So this has the nice behavior that the density winds up being approximately constant when r goes to 0. And we showed before, just from very simple arguments, that would give us and reproduce for us this v proportional to r. And we said that at very large radii, a becomes insignificant. And so we wind up having the density go like some number divided by r squared, goes like 1 over r squared. If we integrate that density to infinity, we would get an infinite amount of mass. That's not really nice. So we talked about some sort of truncation radius of the dark matter halo. And in fact, we wind up sort of intersecting with the dark matter halo of Andromeda. So I think that's what we talked about last time. Were there any questions about last time? People are comfortable with dark matter halos and things that we don't actually see? Okay, that's good. Because today we're going to be talking about how we infer what dark matter actually is. So the nature of dark matter. Just to give you some numbers, remember I said that at 8 kiloparsecs, the density of dark matter sort of around us is about 0.01 solar masses per parsec cubed. Density of stars is something like 0.05 solar masses per parsec cubed. What could be this dark matter? I mean, if you were just sort of starting off and I said to you, hey, there's missing mass, what could it be? It's not accounted for in our normal means.
Stuff that we can't see?
Yeah, so what's stuff that we can't see easily?
Like rocks?
Rocks. Okay, rocks. How would we detect rocks in space, by the way? We need a lot of rocks, but let's just start with that. Yeah.
Really dim stars.
Really dim stars. How would we detect rocks if we really said, I want to detect dark matter astrophysically?
Dynamical things.
That's how we infer that there are space rocks, which are dark matter, if that's what they are. Right? We have a bunch of hypotheses here, and now we're going to sort of test these hypotheses. Yeah.
So you know there's rocks
Yeah.
Already know.
Yeah.
And also, if they were to pass in front of certain things, like, kind of pass in front of things.
Yeah, you can imagine some occultation if if the rocks are like pebbles, right, and we look at a background star and a pebble moves in front, I mean, forget it, right?
Then, where do you draw the line between dust and little rocks? Because I feel like
Sure.
extinction would be
Yeah, so you could imagine that you might detect rocks by some sort of extinction. That's a good idea, or some sort of occultation. How could we rule these out? Well, we see extinction all the time. How do I know they're not rocks?
Well, we don't really, so the rocks are counted in extinction.
We don't know, you're right, we don't know a priori that what we're seeing isn't rocks, but yes.
Extinction is dependent on the wavelength, so that whatever is causing the extinction is comparable to the size of the wavelength.
Yeah, so we have a sense that the stuff that's causing the dominant amount of extinction that we see in the Milky Way, and actually we can do this out to distant galaxies, is actually fairly small particles. There aren't these very big sort of bowling balls or rocks out in space. And the nice thing is we have an estimate for how much dark matter there should be around us, right? So we could just carry that out to some volume. And you wind up seeing that if you put everything in sort of a few centimeter size pebbles or something, that there'd be a lot of gray extinction, that basically we'd wind up taking the light of all stars and sort of dimming them at basically all wavelengths. But it wouldn't be all wavelengths, right? Once I get to sort of a few centimeter size wave bands, I'd see this sort of huge extinction effect, which we don't see astrophysically. So we probably can easily observationally rule out extinction. How about occultation? Sort of hinted at this already. Kind of hard, right? Unless they're truly huge size boulders that have a size that's comparable to the effective size of a distant star in the sky. As these things move in front of distant stars, the star might sort of blink out for a millisecond or 10 milliseconds or something. And we don't actually see that. People have actually looked for small-sized objects in the outer solar system. There was an experiment called TAUS. It was a Taiwan occultation survey. I know what the A stands for. And what they do is they look at something like 10,000 stars, and they look for them blinking out. They actually didn't, in a sort of several-year experiment, they didn't see one star blink out that they weren't expecting because they knew that there was an asteroid moving in front. So actually the number of sort of large rocks out there is actually very small. So it's not sort of small rocks. It's probably not big rocks. So I'll just tell you without us doing the experiment that it's not rocks. Okay, what about really dim stars? How would we sort of rule that out or in?
Well, we'd look near us and see what the distribution of dim stars is to bright stars.
Okay, so you sort of do the demographics. You maybe look very faint. So faint and what we sometimes call deep observations. At what wave bands should I be looking for really dim stars? What? Why radio? Oh, you mean really dim stars? Well, at some point, we're going to wind up getting into this idea, the difference between rocks and stars becomes sort of indistinguishable. At radio wave bands, what we may actually see is emission from rocks, right? And those would likely be in the radio or the submillimeter, and that's also something that we don't see. But if these are dim stars and they have some effective temperature associated with them, yeah, we might look at infrared because they're probably very red. Because if there's a whole lot of them, they're certainly not blue stars that are burning very brightly on the main sequence. They're probably very red stars that maybe underwent some amount of fusion sometime in their past, and now they're just sort of have this latent heat, and they're just sort of emitting this latent heat. Yeah, cold white dwarfs.
And then with that goes neutron stars.
Mm-hmm. Maybe typical masses of a black hole would be sort of 10 solar masses. Typical mass of a neutron star might be 1.4 Solar masses, typical mass of a white dwarf, 0.5. Solar masses, red stars, 0.07 or something like that. Solar masses, if you go farther down there, they basically never undergo fusion. So there's sort of all these different masses that we might think about. And because we have a mass density, we can then say, well, if they're all in dim stars, what should be the density of those stars on the sky, or the density of those black holes on the sky? These are sort of really dim stars are ones that we can rule out observationally. People thought about this, and what they did is they looked in places where there might be lots of really old, dim stars to just sort of do a full accounting of what they saw. And this is a Hubble Space Telescope image of very, very long exposure over several days, looking very deeply at the outskirts of a globular cluster. So if you're thinking about where red stars might be, red dim stars, looking for those with the Hubble Space Telescope in a very crowded region, essentially just counting up the stars, you might actually go deep enough that you just sort of reveal all these stars that were essentially unseen before. And what they did is they did this full accounting of it, and there was indeed no extra population of red stars. People have done this in other fields, not just in globular clusters now. This is one of the first observations that said, red stars are very unlikely to be a dominant source of dark matter. We know about the sort of normal life cycles of stars to the extent that we can look at globular clusters, for instance, and just count the total number of white dwarfs that we wind up seeing. Or we could count the number of young stars that are being formed within the galaxy and look even at distant galaxies that are starting to make their first stars, or their maybe second or third generation of stars. And we can ask, given the luminosities that we see from these new stars, if every single one of them turned into a neutron star or a black hole, or for the lower mass systems, when they're born, they'll turn into white dwarfs at the end, how many would we wind up having? And you can do that sort of work, and you wind up showing that the number of white dwarfs probably accounts for something like less than 10% of this missing dark matter. Black holes, much less than 1%, just by sort of doing the demographics of how we think stars are born and how they die. Really red stars is less than 6%. This is all sort of observational numbers. And where are we missing? Neutron stars. Yeah, neutron stars are also much less than 1%. This is sort of using theory and some mix of observation, assuming we know how stellar evolution well enough. But this is a little bit, on this particular stuff, especially with black holes, is really unsatisfying. I mean, we know that black holes radiate, right? They radiate Hawking radiation. But at 10 solar mass black holes, Hawking radiation we saw is incredibly low. We saw in previous problem sets that likely what we need to do to see an isolated black hole, because again, if all the black holes were in binaries, we can just count the number of X-ray binaries, and we can just say, oh, there's only a few dozen of them that we see in our galaxy. Maybe we're missing a couple hundred. That's not nearly enough to make up this missing dark matter, right? So we're really hoping to see isolated black holes. And isolated black holes accrete the interstellar medium, and we came up with a luminosity for that. And we basically don't see that. We've never seen an isolated black hole. Yes?
Is this for the Milky Way or for a typical galaxy?
This is for the Milky Way. We're going to use the Milky Way as sort of our native laboratory for trying to make these observations. Because here's the place where if it is a black hole, we can throw everything at it, and maybe we'll have enough sensitivity actually to detect the event horizon, right? Because we'll see that there's just black in that part of the sky. People have been thinking about ways of sort of inferring the nature of dark matter by observations of other galaxies, but this is kind of we're thinking today about the most direct ways of doing that. All of these things are called massive compact halo objects. which has the nice acronym of MACHOS. And I'm actually a little bit touched that you all, as proto-astronomers, decided to think about astrophysical objects. Because if you're going to sort of pack in a lot of missing matter, why not do it in some sort of compact object that's not radiating? It's very sort of reasonable. This is sort of a whole genre of possible dark matter particles or objects. The other genre is a direct sort of knock at that, which is weakly interacting massive particles. WIMPs. So we have WIMPs and machos. Who said that physicists and astronomers don't have a sense of humor? Many people. Counterexample there. So WIMPs are weakly interacting. Why do they have to be weakly interacting? Because we can't see them. I mean, if they were strongly interacting, what's an example of a strongly interacting particle? Proton, electron, even a photon, which carries some amount of energy associated with it, and energy is mass density. We didn't say that this stuff had to actually have mass that I could put down on the table and weigh, right? It could actually be something which is moving at the speed of light, and there is no sense of what a rest mass is, but there's an energy. But when there's energy density. You all know intimately well from GR that it doesn't really matter. If I have a parcel of energy or a parcel of mass, it's going to curve space-time in the same way. So it could be that all this stuff is just very rapidly moving at the speed of light, or almost the speed of light, stuff. But what we know about it is we just can't put an apparatus on the table and then just see a whole bunch of these dark matter particles. If that was the case, people would have discovered it in like 1923, right? So it's got to be weakly interacting, and it's got to be massive because there's got to be a lot of it around, right? If these are very sort of wimpy, wispy kind of particles, then even if there's a lot of them around and they're a new particle that we haven't thought of, they might still not make up enough of this missing mass. So neutrinos are a prime example, and for a long time people thought that neutrinos actually could do this. The problem is, only observationally in the last few years have people started really realizing that neutrinos don't have enough mass. We actually know from some of our calculations from the Big Bang how many neutrinos there are around us. We certainly know how many neutrinos there are coming from the sun, because you can calculate, given the sun's luminosity, how often is the proton-proton chain reaction happening, and given that, what's the sort of total release of those neutrinos, and you can just sort of guess at that, right? It turns out that neutrinos have very low mass. We don't know if they have zero mass, but they have a very, very low mass. It's something less than 0.1 electron volt, putting these all in units of energy. Remember, this is just mc squared. Could be some unidentified particle that's sort of beyond the standard theory. And there's a whole class of these things called axions, neutralinos. These are sort of extensions of standard theory and particles that must exist in these theories. Neutralinos are sort of pretty neutral. Neutralinos. I almost got it. This is some sort of relic of a supersymmetric theory from quantum field theory. We don't have any idea or any constraints observationally on what these things are. Just in sort of some beyond extension of the standard particle theory, these particles should exist. But we don't actually know what their mass is, or likewise what their energy is. So what we'll talk about sort of in the first half of the lecture today is are ways of trying to detect massive compact halo objects. We've already talked about dim stars. The important point is that all of these, maybe rocks aside, are very, very massive, right? We're talking about orders of a solar mass. and they're very compact. And if they're truly around, because we can figure out what the space density of these are, just if these things are all in sort of one solar mass objects, this tells us immediately that we wind up having about 0.05 per parsec cubed. Right? So if I had 20 parsec cubes of volume, I'm going to have one of these objects. That's pretty pervasive. Right? There should be a lot of these around. The important point about dark matter on these very massive scales is that they interact gravitationally. We know that, by definition, that's what those objects are. So if I start talking about them in units of sort of one solar mass and they're really compact, there's some clever things that people have thought of to be able to detect these things. And one of them is called microlensing, which is related to what we saw when people were trying to test general relativity, looking at how light curves around a massive object. So detection of machos from an astrophysical perspective, I already told you that we can kind of rule them out just using theory, but that's not very satisfying. What if I wanted to actually detect an object that I can't actually see? You look at its gravitational influence on its surroundings. As I said before, if it's a black hole in a binary, we're going to see stars which have these really strange velocities, right? They're going to have this Doppler velocity going back and forth. There'll be some unseen object around it. We'll be able to figure out the mass function just from Kepler's laws, and we'll be able to figure out sort of what the lower limit is on the mass of that unseen object. We do this often with X-ray binaries. There's just not nearly enough of them. Those unseen objects are either black holes or neutron stars. When we count those up, nope, sorry, not enough. Dark matter interacts only gravitationally. That's the most secure statement that we can make about this stuff. And if it's in large chunks, then they could lens background objects. So just to give you a small cartoon of this, and then I'll show you some more detailed pictures and some actual observations. Here I have a background star that I'm looking at. I have some dark particle which is moving by, very massive dark particle. And if it happens just to sort of pass very close to the line of sight, well, if it passes directly in front and it actually absorbs light, then we might see that star disappear. We do see occultations of stars, but there's not nearly enough of them for that. But if it's actually bending light around it, this light ray, which was otherwise on its way not to meet us, actually winds up getting bent and comes to our eye. And another light ray also winds up getting bent around it. And what we see is, if we're looking now at the sky, we would see two images of that star. Actually, you wouldn't lose all the light from the star itself, but we'd see two images of that star. It turns out for the configurations of dark matter lensing a star within the Milky Way or within a distant other galaxy, not so distant, but nearby galaxies, that the separation between these two images is much, much less than an arc second. In fact, the separation is micro arc seconds. So 10 to the minus 6 arc seconds is sort of the typical number you get for a solar mass dark matter object and for a star which is at a few kiloparsecs away. So this whole effect is called microlensing. And yes?
Why would you only see two images, not like a...
You could see a ring, right? So if I sort of rotate this whole thing around in this way, you can indeed see a ring. That's called an Einstein ring. We don't usually see it in these configurations. You see this when whole galaxies are lensing other galaxies behind it. You can, because it's such a large scale, you can actually resolve this on the sky. The exact location of these two images depends very sensitively on what the gravitational potential is around this and what the exact sort of what's called impact parameter is to the line of sight of that background star. So the location of these images on the sky is actually changing as this thing is moving around. Because we can't see these two images, how does this effect actually manifest itself? Basically, we see an enhancement of the light. We see an effective amplification, because it's as if we're seeing two images of the star, so it's actually doubling the light. And in fact, there are configurations such that when you get that sort of ring structure, you get a huge enhancement of the light. If this was a point source, like a physical point source, and it had mass to it, you would get an infinite amount of enhancement. But because this has actually some size and shape to it, which we might not know, you actually just can get very large amplifications. So the idea here is you look at a star, you have a dark object which moves in front of it, and all of a sudden that object gets bright, and then it gets faint. Yes?
So it's lensing by pulling rays of the star that would be going off and not coming to Earth into us. So how could you get an infinite amplification like that? Couldn't you only get up to the total luminosity put out by the star? Oh, concentrated in one. Got it.
Yeah, concentrated in an infinitely small area towards just your eye, right? So I mean, you can get very large amplifications. You get amplifications of hundreds and sometimes thousands. So you see a star which, might have some magnitude, and all of a sudden it gets brighter by 10 magnitudes. Yes?
Maybe I'm not understanding exactly, but I still don't understand why, in the case that it's not like a galaxy glancing another galaxy or something, why they would have to choose two directions to have the light bend and not always be forming a ring. Seems like it should always.
No, a ring is when you have perfect alignment, right? And it's a perfect point source. But especially with a galaxy, you have a potential which is not actually just spherical. It could have some sort of, it's called triaxiality to it, so it has some sort of direction to where this potential is strongest. And then you get very strange configurations of, basically think about these light rays moving through a sort of complicated lens. Think about, actually one way to do this is if you take a wine glass and you look at a bright light from behind it and you move that in front, you move the wine glass in front, you'll see that little ring for a short time if you move it directly in front, but if you don't, you'll see two images of the light source basically through the whole process. So this is basically what I've just been saying, kind of drawn out a little bit better. We see that star when it's sort of very close to the perfect alignment. Then we'll see that star being lensed. And then later on, as that dark object moves out of the line of sight, it goes back to where it was before. So you can imagine some baseline level, some amplification, and then it's gone. That's some real data. This is just some random star that was being observed by a project called OGLE, where they were looking at the bulge of the Milky Way. So they were looking at lots of stars, because you need a large number of stars. And they just saw this one anonymous star. This is over the course of, this is 200 days, so this is about a year. Another year was just sitting there. And then all of a sudden it goes up, and then it comes back down. And you can see its magnitude changed from 16.5 to 15.5. Got brighter by 1 magnitude, basically a factor of 2.5. And it has this very characteristic behavior where it sort of rises, and this is a quadratic on the rise. It has some sort of top off, and then it winds up coming back down. What's interesting about microlensing just from a historical perspective is that Einstein, when he thought about what's now a classic experiment that Sir Arthur Eddington did in 1919, where he was sort of imploring all these astronomers to go out and measure the locations of stars during the total solar eclipse. Very soon thereafter, he thought about, and he knew, of course, that there would be this sort of amplification effect with stars. But he really thought it was so silly, because how would you know ahead of time to look at that star and watch it get bright? So he actually believed that there was no way that we'd ever see this. And in fact, there was essentially a crazy dude who kept showing up in Einstein's office and kept telling him, you should write this up, this is really interesting. And Einstein actually decided, okay, I'll write up this sort of microlensing idea. There'll be this amplification. And he writes in the paper this crazy dude is crazy. I'm just doing it so he doesn't come back to my office. But it'll never, ever be, this effect will never, ever be seen. This idea was largely forgotten. It was sort of revisited once in the 1960s. And then in 1986, there was a professor in Princeton who realized that because of the advent of digital detectors, so CCDs, the same sorts of things that you have in your cell phones and your video recorders, the ability to sort of digitally detect light across a very large field, even with a small telescope, he realized that you could actually look for microlensing. And to do that, you'd have to look at millions and millions of stars simultaneously. So the Ogle experiment is actually was created because of this guy, Boden-Pyszyński's idea, and it started a whole revolution. People looked not just at the bulge, but they also looked at the Large Magellanic Cloud. And the idea here is if you're going to look for a large sort of broad swath of background stars, you want to do it in places where there's going to be lots of stars, right, and a high density of stars. Each one of these tiles here is an image, a location of an image that this small sort of 1 meter size telescope took. And what they did day after day, or night after night actually, is they just went tile to tile to tile to tile to tile. And they just took an image, they're there for a minute, go to another one, another minute, another minute, another minute. And they just did this for years. This is the entire project, monitoring stars. Now, stars vary. We know about the Cepheid variables and R-Lyrae variables. They saw many of these things. They saw binary stars. They saw stars which actually had strange flares. But it's that special characteristic change of brightness that they were looking for. And they found many. They're now at the level of finding a few hundred a year of these microlensing events. This is a little movie of actually what you wind up seeing. So let's look at the top one just for a second and look at this, this sort of red circle moving forward. This is in sort of weird units here. What we see is the background star is actually the red circle. So in some sense what we're doing is we're kind of tracking the foreground star, or the unseen foreground star. The amplification that we wind up seeing, so this background star is lensed into these blue sort of strange little ellipsy things. And you can visualize this again. Take a sort of wine glass when you're home, and not that you drink wine, but and then move it over a background source, and you'll see that sort of characteristic behavior where you have something going up, and you see this sort of almost a kind of a rotation of these two different images. And you see the alignment isn't perfect. The green circle is what's called the Einstein radius, which can be in angular units. And what we see is the amplification is this amount of stuff. It's the total area of the star on the sky, the two sums of those areas, divided by what it was before. What do you think this little blippy thing is here?
Another thing that's on the sky.
Yeah, and is it associated with the foreground object or the background star? Yeah, it's associated with the foreground object. This is a very, very fast little, extra little blip. And this is a typical signature that you might see from an exoplanet. If you had maybe a dark matter object, or maybe it's just an ordinary red star that's actually faint that you can't see, it happens to move in front of a background star. If that has a planet around it, you now have sort of two sort of mass perturbers, and you have a very strange lens profile, right, where you have all the light rays moving through this strange potential. And you can get not just amplification from the main body, but also amplification from this other little body. So this is actually an entirely new way of finding extrasolar planets. And the first extrasolar planets were found through microlensing just a few years ago. Let me give you some of the characteristic timescales associated with this and for a given mass. And then I'll sort of cut to the chase. tell you what we know about machos as a whole through the microlensing experiments. So here's some flux, and we have some star, background star, whose flux is basically unchanging with time. It winds up getting amplified, and then it winds up coming back down. So this is maybe in units of 1, 5, 10. So this would be an amplification of 10, which would be a very nice amplification. This thickness here, sort of the half width, that's half down from this peak of the amplification. This is the total amplification. This peak here is called TE for Einstein, and TE is of order 0.2 years, and it's scaled by the mass of the dark matter object to the 1/2 power. The distance to the lens divided by 10 kiloparsecs to the 1/2 power times this quantity 1 minus the distance to the lens divided by distance to the source, the 1/2 power, and then the velocity divided by 200 kilometers a second to the -1. So let's just look at this for a second. The distance to the lens is something that's not really known because, I actually can't see this lens object. The distance to the source is something that's in principle knowable. If I have the quiescent value of the flux, then, and I can take a spectrum of it perhaps, maybe after this event is over, I can say, oh yeah, that's an M5 star. So given its absolute magnitude, give its apparent magnitude, now I know what its effective distance is. So that's something that I could know. I certainly can't know the velocity of the object that's moving in front relative to the object moving in back, but you can sort of take a guess at that for different configurations. And you also don't know the mass. So there's kind of 3 parameters here, the unknown mass, the unknown distance to the lens, and the unknown velocity. But you can get some guesses at this. In fact, there's some clever ways if you watch this microlensing event from 2 different places on the Earth, you actually see the events happening at slightly different times, and they get slightly different characteristics. So you can get an effective parallax to this lens object. This lasts for most of the lensing systems we see much less than 0.2 years. They last more like sort of 20 days. And so for these typical numbers, if those other things are right, it means that the mass of the typical object which is doing this lensing is actually smaller than a solar mass. Yes?
Is that TE measured right at the maximum of that amplification?
No, T is the sort of characteristic duration of the lensing event. And so you can imagine that even though I don't know all these things, I can sort of have some guesses at what they are. And in a statistical sense, I might not know the exact mass of a given configuration, but if I now have hundreds of events, I can start kind of pulling some of this stuff out. And this is what was done by an experiment from someone named Charles Alcock. He was a postdoc here at Berkeley, now a professor at Harvard. And this is sort of one of the most impressive figures, it might not look like that, in what they did with these machos. This is a fraction of the total amount of mass in machos as a function of the total amount of dark matter that's required by a rotation curve. So if it was 1, then the machos would account for basically all of the dark matter. Because we don't know exactly what the mass was of a given event that we're looking at, if you look at the typical masses going from 0.01 solar masses up to 1, you can draw these contours of certainty or uncertainty. And the sort of best bet is that only about 10% of the total mass of the dark matter is made up in these machos. And the typical numbers for the masses of objects that are doing this is something like 0.03 solar masses. So these are red, sort of very low mass stars, and there's a whole lot of them, and they're doing most of that microlensing. So this is one of the most important sort of astrophysical non-detections of dark matter, because it really just says it really can't be in compact objects. If they're in binaries, we'd know about them. If they're isolated, we'd see them. And they were able to rule out essentially 99.9% confidence eventually that these things can't account for all the dark matter. It has to be something else. They account for a little bit, but not all of it. Just a little bit of an aside in the context of planets. Here's a strange lensing event from 2003. You can watch the object go. That's basically real data. You can see these sort of very short timescale events are really short, so you have to catch it. And how do you get that? Well, you've got your planet and your lens star, and it moves in front, and you get these sort of crazy configurations of the lens as viewed by you down here, and then it's over. See if I have any more on that. Do people want to see a little more on that? You like microlensing planets? Okay, I realized that I had those turned off. Yeah. Here's an event that was incredibly bright. It was something that I looked at with one of the telescopes that I basically operate. And this was an incredibly bright amplification. And the non-detection of any extra little blips is actually a way of ruling out the existence of planets around that object. But this is one of the most famous events now. It's pretty complicated. This is the light curve. So I-band magnitude, it's sort of quiescent values, a little bit fainter than 16th magnitude. At peak, it got to 14th magnitude. So not a particularly very interesting event, except they wound up seeing a couple of extra really strange blips around here and a couple other strange blips over here. And this allowed them to find not just one planet, but two planets that have the mass of Neptune, basically two Neptune mass planets that are at several astronomical units from this star. So these are all these strange extra little events, and you can see the model fit to that. You can see just how much data is required to get all that. Anyway, planets are not also dark matter, but I thought I would just tell you that. Okay, so the upshot is that there are several events found through this microlensing technique. It is really the cleanest technique that we can think of, knowing only that machos would interact gravitationally. Several dozen events found in the early 90s, and now we're up to probably about 1,000 microlensing events. A few hundred a year. And doing all the sort of hard statistics on this, they found that the mass in dark matter is much less than, or at least less than, the stellar mass inferred through lensing. So our theories of how we take a star and we wind up turning it eventually into a neutron star, and we count the number of A stars now, that gives us a sense of how many neutron stars we have around us from previous A stars. That kind of thing all turned out to be about right. There's not an extra amount of these very massive objects that we didn't know about. One of the things that I wanted to point out is that the stuff that makes up machos in an astrophysical sense are all baryons, right? The stuff that gives them mass is not just a big ball of roaming electrons, but it's protons and neutrons. We know a lot actually about baryons, or we think we know a lot about baryons and how many baryons there are out there. not just because we can count up the total amount of gas in the Milky Way, but because we can actually look at sight lines to distant quasars. Remember, quasars are these very bright sources of basically a supermassive black hole that's accreting a lot of material. If a quasar happens to be piercing through a foreground galaxy, we can study the gas in that foreground galaxy. It turns out in a few of these sight lines to certain very bright quasars, we've been able to make measurements of the amount of hydrogen in a given gas cloud and the amount of deuterium. Deuterium is never really made in stars. It's only used in stars. And so if you can make a measurement of a cloud which you believe to be sort of primordial, that is untarnished by the sort of stars around them, and you figure out the ratio of the deuterium to the hydrogen, you get a measurement of the ratio of deuterium to hydrogen as created in the Big Bang. And it turns out people can do this with lithium and beryllium, and you get actual measurements of that ratio. We'll see in the sort of last week of class when we talk about baryogenesis and Big Bang nucleosynthesis in general, we'll actually see that the observations of deuterium, beryllium, and lithium are all in agreement with the nominal expectations that you get by looking at other cosmological phenomenon. That is, we can make a prediction. We can look at the sort of way in which galaxies are moving away from us, and we can make a prediction of how many baryons were made. We knew, in fact, if we didn't have this microlensing idea, we would have been able to rule out baryons as a potential for this dark matter stuff, because we would look observationally and through cosmology and theory, we'd be able to rule that out. So this idea of using microlensing was a great one because it's something we can test just locally, but it actually also fit with what we now see observationally, that it just can't be baryons. There's a little tiny bit of a clever way to wiggle out of this, which is to say that you put all the mass in sort of comet mass, or 10 to the 15 grams or so material in tiny black holes. And the way that you do this and the way that you get around this sort of baryogenesis constraint and the total numbers of protons and neutrons in the universe is that you make these black holes before you actually made baryons. So you do this in the very, very early universe. You make these tiny little black holes. And then these black holes haven't evaporated yet, so they're still around. They're just now starting to evaporate. And if you do that and you sort of cook the books, it's possible that you could have lots of these 10 to the 15 gram little tiny black holes around us. How big would a 10 to the 15 gram black hole be? Well, you can just scale from the sun, right? What's the mass of the sun in grams?
33 grams.
Yeah, something like 10 to 33 grams. This would be, and what's the Schwarzschild radius? Yeah, a few kilometers. So this would be 10 to the 33 divided by, what did I say, 10 to the 15 grams? Actually, to the -1 times a few kilometers. 10 to the -18 kilometers. So the Schwarzschild radius of one of these black holes is tiny. And in fact, if one of them passed right through you, you wouldn't even notice. Kind of weird. I mean, you'd notice because maybe like the chair would move a little bit or something. So this is the one way to wiggle out of actually putting them in fairly massive objects. But we really have no great way to test this sort of intermediate between WIMPs and machos. Okay, sorry, that was a bit of an aside. All right, so any questions about machos and how we know about machos as not being the prime dark matter candidate anymore? All this is fairly new, right? So if we took this class 15 years ago, we'd say it could be that they're in black holes or they're in neutron stars, and we'll find out after this Alcock experiment is finished. Yes?
Wait,
Pauline.
so is there some kind of theory for how these primordial black holes form?
There isn't a theory, but people are kind of okay with it because what is a primordial black hole? It's just a, sort of an extra amount of high density in a small region of this very expanding universe of energy. So this is before electrons were around. It was just pure energy. So if I take pure energy and I sort of bunch it up and I make a high density of pure energy, and I wind up getting enough energy within the Schwarzschild radius of itself, it's a black hole, right? So we have no theory for what the distribution of mass should be of those black holes. You know, people can kind of come up with that, but that's sort of beyond the kind of thing that we have access to, that we can't even see cosmologically what that might be. But there are sort of toy theories that people have been thinking about since the 1970s. Okay, so let's talk about WIMPs. As I said, neutrinos probably aren't massive enough, so now we want to figure out how we might make measurements of WIMPs. Well, I mean, the short of it is that you look for WIMPs not interacting at all, but actually doing their weakly interacting thing with ordinary matter. So the idea here is that you have some particle, it has mass, it winds up passing through some big thing in your detector, and somehow you get enough of these things passing through that one of them just says, okay, I'm going to interact with ordinary matter and I'm going to make you happy. And then it interacts with that ordinary matter. You capture everything you can about it. Perhaps if it's in some sort of crystal, you can imagine that it winds up sort of doing some ionization because it might interact with a nucleon and rip the nucleon apart from the electrons. And you could actually see some sort of ionization trail. You can imagine that if it actually pushes the nucleon, that the nucleon sort of bounces back and forth, and it actually creates what's called a phonon, which is basically a sound wave propagating through this crystal. And you try to make very precise measurements of all these interactions that happen. The problem is, as you can imagine, you've got this weakly interacting particle, and it's in this soup of very interacting particles, even muons and even neutrinos that are coming from from cosmic rays, from the sun. Those things, they may be not that strongly interacting, but they're probably even more interacting than these dark matter particles. So you have to make this measurement in the presence of a crazy amount of noise. The Cryogenic Dark Matter Survey, CDMS, at Berkeley is sort of one of the leading laboratories to find dark matter. And the idea is simple. We have a dark matter particle. It interacts with a nucleon. They look for these interactions in phonons and in ionization trails. And there's some theory that predicts approximately what the cross-section is. This is beyond standard physics theory, so take that with a grain of salt. But the typical numbers that you wind up seeing is that the cross-section for a dark matter nucleon interaction is something like 10 to the minus 48 meters squared. That's 10 to the minus 8 picobarns. Does anyone remember what this number was for when we're talking about Strömgren's sphere, when we're thinking about the recombination rate when I have an electron and a proton? Yeah, 10 to the minus 24 or 10 to the minus 25. So we're 10 to the 24 times less than the typical interactions that you get between an electron and a neutron. So this is the advertisement for their website. Not a very flashy website. Bernard Satellite, a physics professor. And they've had some experiments where they've been able to figure out, this is a very complicated graph. I'm not going to test you on this. I just thought I'd show you some of this stuff. Here they put the WIMP nucleon interaction in units of centimeters squared, so sort of typical numbers that I had before. And these are their best values that they've been able to get. Now, they need to know what the WIMP mass is, because that's going to actually dictate what the interaction is as well. And so in this sort of interesting scale of something like 100 giga-electron volts, so obviously much more massive than a neutrino. I said that was less than 0.1 electron volts. They've been able to put all these interesting limits. And the stuff that you see up here in black and green are sort of theories that people have put out of where the WIMP particle could actually live. And so they started carving out a reasonable amount of parameter space, and they're hoping to push farther and farther down as they go on. Let's figure out how many of these dark matter particles there are around us, because they said that hopefully there's enough of them that they're streaming through enough of material that I could detect a few of them. Okay, so let's do neutralinos. The theory predicts that they have a mass between 50 and 200 giga-electron volts, divided by c squared, of course. Let's figure out what that is. So let's make it 100 giga-electron volts. Giga is not 10 to the 6, it's a billion, so 10 to the 9. 100 of that is 10 to the 11. Electron volts, that's 1.6 times 10 to the minus 19 joules per electron volt, just to convert it into units that we know. Divided by c squared, 3 times 10 to the 8 meters per second squared. So that's 10 to the 16. That makes this, in the denominator, 10 to the 17. We have 10 to the minus 19 here. So we're going to more or less, well, let's make that 10 to the minus 8. So what does this turn out to be? About 10 to the minus 25 kilograms. So that's, when we talk about giga-electron volts, that's sort of a typical number. Not so different from a proton, right? So these have a typical mass of that. All right, so let's figure out, now going back to our dark matter halo. Remember, rho of r of the dark matter is equal to C0 a squared plus r squared. If we put in the numbers that I gave you before, 5 times 10 to the 8 solar masses per, I think, was it kiloparsec or parsec? Yeah, kiloparsec squared divided by 2.8 kiloparsecs. These are the numbers that I gave you previously. Plus, let's put it out where we live now, 8.0 kiloparsecs. We can come up with a number. This turns out to be, without doing all the math on the board, 7.0 times 10 to the 6 solar masses per kiloparsec cubed. And if you put in the numbers and convert kiloparsecs to meters and the solar mass to kilograms, you get 4.7 times 10 to the minus 22 kilograms per meter cubed. Excuse me. All right, so this is cool. We have a mass of a neutralino, of a dark matter candidate. We have density in mass units. Now, if I want to figure out the total number of these dark matter particles per meter cubed, how do I do that? That's just rho of the dark matter divided by the mass of the dark matter. Ten to 4.7 times 10 to the minus 2 divided by 10 to the minus 25. If I put in carry all the numbers correctly, I get 300 per meter cube, or 3,000 per meter cube, excuse me. So in every meter cubed, at any one time, there are 3,000 dark matter particles. That's sort of a well, of order the volume that you take up. There are 3,000 dark matter particles in you at any one time. If we want to think about how fast these dark matter particles are moving, what do you think a reasonable number might be? Remember, these dark matter particles don't care about you. They don't care about Cal. They don't care about the CDMS, it turns out. They're just streaming around, right? And they're part of this dark matter halo. There's going to be a characteristic velocity associated with a dark matter halo at 8 kiloparsecs. Of all the velocities that you know about, what do you think a typical number might be of how these things might be moving? What's that?
Like an average?
Yeah, an average thermal velocity. But the thermal velocity, if this stuff is all in some sort of virial equilibrium with the motion of the stars in the galaxy. Yeah, that's a good number. Not that I was being too leading. So it's thought to be that the dark matter stuff is all part of this halo, right? So they're just sort of streaming around in all these random directions, but they're part of the dark matter halo. They're in some sort of equilibrium gravitationally with all the other stuff, the ordinary stuff around it. And so they're probably streaming through you at 220 kilometers a second. So the flux through you is going to be proportional to what? Surface area flux is some sort of number per unit time.
Number density and velocity.
Yeah, number density of the dark matter particles around you and the velocity of the dark matter particles. I mean, it has to be that dimensionally, right? It's got to go as I increase the velocity, that flux has to increase linearly. As I increase the number density, that also has to increase linearly. What's a good number for a surface area of a spherical person? All right, 1. Good, order of magnitude. Yeah, it's about 0.5. Yeah. Number density, I said, is about 3,000. 220 kilometers a second. If I want to do this in meters now, so this is per meter cubed. What is this in meters? Scientific notation? 2 times 10 to the 5th meters per second, something like that. So what does this turn out to be? This is like 3 times 10 to the 3. So this is like 6 times 10 to the 8 per second. So there's roughly 1 billion dark matter particles moving through you every second. Yes?
So like this number density and stuff, this is just like assuming that all the dark matter is in neutral windows?
Yeah. Because if you're trying to figure out an experiment, you need to know what this flux number is. And of course, there could be a distribution of masses, right? This neutralino mass is the lightest of the 4 neutralinos that's stable, blah, blah, blah. There's a whole sort of extra supersymmetric theory that sort of describes what the relative masses of these neutralinos are. And there's some thought from Big Bang theory that tells us it should be in this sort of range here. This is just a pure guess, though. If it turns out it's a tera electron volt, no one's seriously wrong. It just means that they just didn't think about something. So this is assuming they're all exactly the same mass. It's assuming that our central fits to the rotation curve is a way to tell us about what's going on locally. And that gives us our number density, figure out the flux through anything, and that's what you get. So there's a lot of that stuff, and none of you have ever interacted with dark matter that you know of. Yeah?
Is using the velocity as 220 kilometers per second okay because aren't we also moving at that speed?
Are we moving at that speed?
Yeah, around the center of the galaxy, right?
Yeah, but are we all? So is everyone? So think about it. If that was the case, then the dark matter halo would have to be also co-rotating with us, right? So maybe it is co-rotating with us, and then we would have the relative velocity be 0. But is that exactly right at all times?
No, but I think it would
It could be less than that. Well, so here's what the CDMS is doing. They're recognizing that if it's not that you've got this static, which seems a little bit like an ether, but you've got this static sort of fluid of dark matter stuff that's out there, and we're moving through it, because we're around the sun and the sun's around the galaxy, and we're moving 220 kilometers a second. Even if that's not true, think about if we're all co-rotating together, dark matter and the motion of the sun. The Earth is actually moving around the sun at something like 30 kilometers a second, right? So the relative velocity to this overall bulk flow of that could actually indeed be, instead of 220, it could be something like 30 kilometers a second. So what CDMS is doing is not looking for a total number of hits, because they get a lot of them. They're looking for a seasonal variation of those hits as the Earth moves around the sun. So this smells a lot like the Michelson-Morley experiment, where they're looking for seasonal variations of the speed of light. But now the CDMS and their competitors are looking for this. There was a report that one of their competitors in Italy actually saw this seasonal variation. And no one's been able to sort of rule that out from that experiment, but people have essentially redone it and not seen that same seasonal variation. So they don't know why that was. Maybe the voltage on all their equipment was changing seasonally. No, I mean, that's all the stuff that they have to worry about. Okay, but you're astronomers and you care, I guess, a little bit about particle physics, and you've just realized that machos are not the answer. You're interested in knowing about astrophysical ways to figure out what these WIMPs are. What's an astrophysical way that you might think about WIMPs?
Different emission and absorption that you previously, I think.
Yep, it could be some sort of emission or absorption. They're not strongly interacting with ordinary material, right? And even if they were, if they hit some proton, how do you know that proton wasn't actually hit by, an electron? We look at sort of aggregate and sort of over the whole sky, we might try to look for a signature. The idea here is that if you have these neutralinos, these dark matter particles at 100 gigaelectron volts per c squared, then if they wind up annihilating with each other, that is, they wind up having a cross-sectional interaction that's actually reasonably big, because I presented to you what theory tells us about what this cross-section is with ordinary matter, but what's the WIMP cross-section? It could be large, right? It could be that they actually like interacting with each other. When you have two WIMP particles smashing into each other, there's going to be a cross-section associated with that. That cross-section will be some number. You'll have some number density, which you can figure out from the halo parameterization. And when you have annihilation, you actually smash these things two together. It could be that you create some other dark matter particle, and then that's really troublesome because we're going to have an even harder time of measuring that. But what it could be is that they actually release light. If you have an electron and a positron and they smash into each other, you get the inverse of pair production, right? You basically get two photons. If you have sort of gigaelectron volts or tens or even hundreds of gigaelectron volts things smashing into each other, and they're producing typical energy photons, those typical energy photons are going to be around the same energy, right? And those are gamma rays. So there is a theory that tells us for a given cross-section, we might actually be able to see the annihilation of dark matter in the center of our own galaxy by looking for some sort of extra gamma ray emission. And the gamma ray emission wouldn't look like the other type of gamma ray emission that we see from all the other processes. It might have some characteristic spectrum or some characteristic line. And it could imagine that you wind up getting a line which is exactly the mass of one of these neutralinos. And in fact, because they're dark matter halos, this is actually one of them, and here's another one, you can imagine you actually get little clumps of annihilation of material from our galaxy, and then we look at other galaxies, maybe that. So this is something that was potentially seen recently. This is really hard to understand here, but this is the Milky Way that's been sort of cut out because there's a lot of gamma ray emission from there. In the 10 to 20 gigaelectron volt, doing a lot of sort of post-processing on an all-sky map from this satellite called Fermi. This is sort of a better picture of that. There's this extra sort of gamma ray stuff coming out. One of the things you notice, well, what do you notice about this? First of all, does everyone see what you're seeing here? You're seeing in the way that I've been showing you the Milky Way when we're talking about the interstellar medium, we're talking about carbon monoxide maps, etc. This is the galactic center this way, B equals 0, L equals 0, and L going out to 180, coming back around here, and coming through here to 360. This is negative B down to negative 90, B up to 90, right? So this is just a projection on the sky. And they've removed all these extra sources and things that we already knew about. There's a little bit of emission here, which is probably related to supernovae remnants. And then there's this extra stuff, this plume. What might you expect about sort of a dark matter halo, which is sort of an equilibrium, because the Milky Way isn't really being perturbed dramatically? You might expect it to be uniform, or at least sort of semi-spherical around this, right? Because the distribution of mass is actually reasonably spherical around the center of the galaxy, right? There's this sort of very large bulge that we can't see here. There's actually the disk, but most of the mass is in the bulge and in the dark matter halo. This is sort of too elongated in this direction here, and it's actually asymmetric. So the thought is that this is not dark matter annihilation, although people were very excited about that. But the thought is this is probably some past activity of the black hole at the center of the Milky Way, which was at some point an active galaxy, and it spit out a lot of particles along its axis, in the way that we see many other galaxies do. And so the depiction that NASA would have you think of, and this has now been seen at X-ray wavelengths, this is X-ray emission. You can actually see a very sharp sort of cutoff, and then this gamma ray plume. The idea is that this is some sort of relic of a lot of energy that was put out from the black hole at the center of our galaxy. So the verdict is still out of whether we're going to astrophysically detect dark matter or not. The only thing we know about dark matter, this is maybe the takeaway message, is that it interacts gravitationally. If it doesn't have any cross-section with ordinary matter, we're in a lot of trouble, right? And it's a small particle. Then we're in a lot of trouble. So hopefully it's got some little cross-section, and hopefully here at Berkeley they'll be able to sort of find a very characteristic and strong signal. All right, so I think I'll end with that. We'll pick up with galaxies and rotation curves of galaxies on Tuesday. The thing to remember, of course, about galaxies is that because we're not embedded in them other than our own, when we observe the rotation curves of other galaxies, it's actually easier than observing the rotation curve of our own galaxy. You'll work on this in section.